Good morning. Good morning because that's the time I'm recording this, not necessarily good morning because that's the time you're going to be watching this. But anyway, this isn't really a new concept. This isn't really a new idea. Being able to do Pythagoras in 3 dimensions simply requires you to be able to see things and to be able to see things in 3 dimensions and maybe be able to sketch things out in 3D. It is not more difficult than what you have been doing before, but it may be tricky if you're not used to it. So what I've got here is just a few examples of where you might find Pythagoras in 3 dimensions. These examples do not cover every possible case, just a number of them. And maybe, if you've never done this before, seeing it now may help you start training your brain to see things and have, where you might apply. I'm going to start with the classic case, the cuboid. In a cuboid, there are multiple different right-angled triangles that you're going to be able to see. The first one is here. It would be, because that is a right angle, even though it doesn't look it, but this side and that side there are at a right angle. Think about the classroom as a cuboid. That's the wall, that's the corner going down, that's the floor. So that's a right angle triangle, and we have one hypotenuse there. So if I knew the height and the depth of the room, I could find the diagonal across the wall. Equally, we have another right angle triangle on the floor. So between this here and the side, there is another right angle triangle going diagonally across the floor. So my right angle triangle is there. Again, think about the edge of the of one wall and the other wall, so it makes a 90 degree on the floor. And there's a third right angle triangle which maybe doesn't again look at, but from the top right corner of the room to the bottom left corner of the room, there is another right angle triangle there, where the right angle, if I erase that one there to avoid confusion, it's there. So between one corner where the 2 walls meet and the corner where the 2 walls meet and diagonally across the floor, that is another right angle. So if I wanted to calculate the length of the longest diagonal of the cuboid from the top right corner of the room to the bottom left corner of the room, I may have to do Pythagoras twice, because I will need that diagonal there, that side, that's my right angle there. So between that and the diagonal across the room, and then this would be the hypotenuse of the right angle triangle. So as you can see, there are multiple right angle triangles in a cuboid. In a cone, and this is what we weren't able to do back in chapter, whatever it was, 12, there is a hidden right angle triangle here. This is the vertical or the perpendicular height of the cone. That would be the radius, so I have a right angle triangle here. So if they wanted me to find the curved surface area, remember, the curved surface area of the cone is pi RL. I need the slant height, but they may not tell me that. They may give me the diameter, 10. They may give me the perpendicular height, 8. So I will have to use Pythagoras theorem in this triangle here to find the slant height and then be able to calculate the curved surface area of the cone. In this triangular prism here, again, we have a right angle triangle there on the side. We also have one diagonally. So we have one here on the floor. That's 90 degrees, and we can find the diagonal along the floor. And again, just a bit like with the cuboid, we also have a right angle triangle which goes, so if I delete that one from before, from the top right corner to the bottom left corner, and the diagonal across the floor So we have that, that, and that, with that diagonal being the hypotenuse. So as you can see, there are multiple right angle triangles here again. And finally in the cylinder, again, I saw a question in the exam once where they gave you the dimensions of a pencil case. So maybe this was 10, maybe this was 8. And I think they asked you something like, would a 9 centimeter pen fit in the pencil case? And you think, well, it's a 9 centimeter pen, it's not going to fit. But actually, it could fit diagonally, and again, that would be the diameter. This is my right angle triangle, and I could do Pythagoras theorem to see if the pen would actually fit in the pencil case. So, as you can see, there's nothing new here. It's just training yourself, training your mind to see right angle triangles where apparently there may be none. But anyway, that's all for today. It's nothing new, just changing the context. Good luck.